The purpose of this video is to demonstrate how normal and shear stresses are calculated in non-rectangular beams. We consider a channel beam with uniform thickness of 1 inch. The beam is 8 feet long and it is loaded by a uniformly distributed load, 1,000 pounds per foot. Our task is to determine the maximum tensile, compressive, and shear stresses in this beam. For a uniformly loaded cantilever beam, there is no need to construct shear force and bending moment diagrams. It is clear that the maximum bending and shear will be at the wall, and accordingly it is sufficient to draw a free body diagram showing M and V. Let me point out that I show M and V as dictated by the sign convention for internal forces. This is helpful because the signs will clearly indicate what should be done when I conduct stress analysis. Accordingly, I can write down basic equilibrium equations and obtain that the shear force is 8,000 pounds and the bending moment is minus 384,000 pounds times inch. I use inches because I'm preparing myself for dealing with the cross section where all the length units are in inches. I start analyzing the cross section by looking at the centroid. So here I show in red and blue the distinct subdomains that will be used to analyzing the centroid. I also introduce the axis Z bar and Y bar. Z bar is located at the upper fiber so that all Y coordinates are non-negative. And I emphasize here that because of symmetry, the two webs have the same property, and I will take this into account in my calculations. So the centroid for the flange is 0.5 inches. The area is 8. And for one web, the centroid is 2. And the area is also 2. Of course, here we have 2 inches and here we have 2 inches squared. Now, when I calculate the centroid of the entire section, I use 2's here, right, to show that I have 2 webs. The end result is that the centroid is located 1 inch below the Z bar axis, which happens to be right at the intersection of the flange and the webs. My next step is to compute the moment of inertia. So now I use Y and Z axis that are associated with the centroid of the entire cross section. I record the areas, 8 for the flange and 2 for a single web. And here comes the parallel axis theory. For the flange, 8 times 1 cubed divided by 12 times 1 minus 0.5, which is the distance between the z-axis of the entire cross section and the z-axis of the flange, times the area of the flange, plus 2, because I have 2 webs. 1.2 cubed divided by 12 plus 2 minus 1. 2 minus 1 is the distance between the z-axis of the flanges of the webs and the z-axis of the entire cross-section, and 2 is the area of a single web. The end result is 8 inches to the fourth. For normal stresses, now I show red and blue not only to differentiate between the webs and the flange, but also to differentiate between compression and tension, because everything below the z-axis, according to the basic formula, will be in compression. Why is that? Because the moment is negative, and so everything for positive y will be compression, and everything for negative y will be tension. Now I can do the calculation for the tension. The moment times minus 1. So that's the coordinate of the upper fiber. That's where the tensile stress is maximum, and it happens to be 48 ksi. And now I'm ready to go to the compression. And in this case, I will use y equal to 2, and I obtain that the stress is minus 96 ksi, or we can say that the compression is 96 ksi. Now let us consider the shear stress. Now we, in blue, show the area below the z-axis, or we refer to this area A star. Please observe that there are two webs, and therefore A star consists of two components. The standard formula could be evaluated using V from the shear force diagram and IZ calculated previously. Now for Q, the calculation proceeds as follows. If I look at one web, then there is Y bar star, A star, and now I have to multiply by 2 because there are two webs. If I look at B, I also have to multiply 1 by 2 because the combined width along this line is 2 inches. With this in mind, I proceed and calculate the shear stress in the cross section, the maximum shear stress in the cross section, equal to 2 ksi. To conclude this example, I would like to point out that if this is our original cross section, there are possibilities for two other designs. In this design, the webs are longer than in the original one, and as a result, the centroid shifts down. So that's how the z-axis look like. The other alternative is the webs are short, and as a result, the z-axis is going through the flange. Accordingly, I can refer to this channel as deep and to this channel as shallow. It happens that the channel of interest to us is neither deep nor shallow, so we call it intermediate channel. Now, if I look at the deep channel, it is clear that when we cut through the webs B is equal to 2 inches, 1 plus 1. In the case of the shallow channel, we cut through the flange, and then B is equal to 8. The question then becomes, what do we do at the intermediate channel? We adopted B equal to 2, which is probably the best we can do with our analysis. We're doing a conservative estimate, but the story becomes a bit tricky, right? Because we really kind of cannot decide whether it's 2 and 8 definitively. And so in these cases, it's a good idea to say maybe we need a bit more detailed analysis for this cross-section to figure out what is going on with the shear stresses at the interface between the webs and the flange.